Part B of Module 2, the topic is data normalization. Yeah. So in this part, we talk about database design issue. So now let's think about, we need to design databases. When we design databases, what is a good way to do it? Yeah. So here, today we consider a few important issues. Yeah. The first question we like to think about, that data normalization, B.1, redundancy problem. Redundancy. Yeah. So here, I think you can guess the meaning a little bit. Yeah, but I need to explain a little more. So what's the redundancy in our database design? Yeah. All right, so first, so let's consider the general redundancy problem. Yeah. Here we are in the situation, we need to design good databases. So the databases can help us implement our web applications efficiently, correctly, then efficiently. Okay, quickly, responsive. Yeah. All right. First, the basic meaning, storing the same data multiple times. That's the redundancy, the same piece of data. So you do not store it only once. You may have a chance to store it multiple times. Yeah. So that's the typical situation for the redundancy problem. Yeah. So then naturally you may ask question first, why we do that? That's the first thing. Second, if it is possible, can we remove the redundancy? So here, two questions. Now, first, why we allow redundancy? Second, is it possible to remove redundancy? So we will answer those two questions. All right. First, the drawbacks, redundancy. So here you can see something, drawbacks, but later you will also see something that could be useful. Redundancy, so that's sometimes we need it. Sometimes we need it. Yeah. All right, so first, the drawback part, duplication of effort. If you have certain redundancy in your database design, you need to pay a little more effort, duplication. All right, yeah. So need to perform a single logical update multiple times. When you need to change one piece of data, but that piece of data could be repeated a few times. So in order to maintain the consistency, we know in the database design, the consistency is important, right? Consistency, right? Suppose you have three pieces. You update one of the three pieces. The remaining two pieces stay in the old value. Then you don't have data consistency in your data, right? Yeah, so we do not allow that happen. Yeah. So in order to maintain data consistency, you have to update everywhere it appears in your database. So that's the duplication of effort. All right. Yeah. So, all right. Wasting storage space. Yeah. Okay. More, you use space more than necessary. Yeah. Okay. All right. So that's the obvious reason. Yeah. All right. Inconsistent data. Yeah. So that's what I mentioned. Yeah. Files that represent the same data may become inconsistent. Yeah. Here, look at this word, file. I like to explain a little bit. Files. Yeah. So I use this word files. You know, what are the files? Okay. Yeah. Yeah. Regular files, the files stored on our hard drive, physical files. Yeah, here, the files in this context. Yeah. Here, I like to, here in our database context. Okay, in database context, its meaning different from our usual understanding of file. Database context, it means a table. One file corresponds to one table. Why is that? Yeah. Think about it this way. Yeah, let me dismiss this little window here. Annoying. Yeah. All right. Think about database develop managed system. Some people, they need to develop that, right? Some people need to write a code to create that software. All right. When those people, they create that database management system software, they need to store many tables in some special format, right? Yeah. They store one table in one individual file. Okay. So that's the internal storage format. One table corresponds to one file in the database management system. Yeah. Yeah. So for that reason, the authors, so when they, talk about in the database context, when you see files, you just interpret the meaning to tables. Okay. Yeah. In other contexts, you should not do that interpretation. Okay. Yeah. All right. Yeah. So a file stored physically. When you see file, all right, so you can, by default, you treat it as a physical storage. Yeah. Physical, all right, yeah. Later, we will see the virtual case. Not physical storage, virtual case. Okay? We have a virtual file, all right, a virtual table. Yeah, that's a later concept. Yeah, all right. Oh, yeah, so that's B.1. So B.1, we just described the redundancy problem. Okay, yeah, very simple. B.2, the concept of data normalization. Yeah, this time we need to think about why we allow data redundancy, right? Yeah, our first reaction, straightforward reaction, we want to remove redundancy. Now, because in the previous slide, we saw three drawbacks, all drawbacks. Nothing is good here. Yeah, nothing is good. So why we need to keep that, right? Yeah. So our first reaction, we want to completely remove the redundancy in our database design. Yeah. Oh, so let's have that discussion. That's called a data normalization, that concept. Okay. First, let me describe this concept, data normalization, the ideal situation. Yeah. Ideal case. Yeah. Store each logical data item in exactly one place in the database. No redundancy. Okay. Yeah. So our first reaction, no redundancy. Yeah. Make our database design perfect. Yeah. Look perfect. Ideal. Okay. Yeah. When you see ideal, then you have a natural connection you can think of, because in our real world, things are never ideal, right? Yeah, when you say something ideal, something you can never get there, all right? So that's like something ideal. You cannot reach that goal. It's ideal thing, right? Yeah. So here, similar. We have a similar situation, ideal situation, okay? Yeah. All right. Logical data item. So you know logical data item. Physically, that data piece is stored in one of the tables. Yeah. A data item appears in multiple tables with different field names for convenience. Yeah, here I describe the typical situation for a redundant piece of data. A redundant piece of data, the typical existence of that piece of data is like this. One physical, the same data item, okay? Yeah, so let's say the first name of one student, just the one piece of data. But for some special reason, we may store that piece of data multiple tables under different field names. We know that that's not convenient, or that could cause some problem. That could cause some problem later. All right, but here for convenience, yeah. So here, yeah. So people may ask why you need to store the same logical data item multiple times. For convenience, for some kind of convenience, but when you need to modify that piece of data, it's not convenient, right? When you need to modify it, you need to keep track of, first you need to keep track of all places that piece of data appears. All places, keep track of. Then you need to maintain data consistency. In that point of view, it's not convenient later. All right. Yeah. So here, yeah. So this convenience, yeah, we need to understand what kind of convenience here you are talking about. Yeah. Yeah. So later we need to elaborate this convenience. Okay. All right. Benefits. Yeah. Something that is good. Yeah. Not drawbacks, this time benefits. Okay. Something could be useful. Yeah. Redundant data. Yeah. Oh, sorry. The benefits for data normalization. All right. So data normalization, that's the opposite meaning of data redundancy. Opposite meaning. Okay. So data normalization, that means remove redundant data. Okay. Yeah. Opposite of data redundancy. So remove completely. Remove. So ideal. So that's the ideal. Data normalization, that's the ideal situation. Okay. Yeah. Now we talk about the benefits of data normalization. First, save storage space. Yeah. One logical data item, only one place. Okay. Only one place. Yeah. All right. Yeah. All right. Easier updates. When you make an update, only do update at one place. You do not need to keep track of all the places for one particular data item. Yeah. So very easy. Yeah. Yeah. Only change one copy here. Yeah. Ensure data consistency. You do not worry about data consistency, right? Yeah. you won't have two different copies. They refer to the same logical data item with different values. So you don't worry about that situation. No. So that's very convenient, right? So that's the convenience we like to have. All right. Yeah. Okay. Yeah. So now the question, should we always make our data normalized? When we design our databases, should we always make our data normalized? Okay, yeah, so that question. Yeah. Okay, yeah. So let's answer the question this slide. The topic is controlled redundancy. Okay, yeah. First, the redundancy, we cannot completely remove it. We need to have certain amount of redundancy, but we need to put control on it. Okay, so we should have controlled redundancy. If it's not under control, it's bad, right? Not under control, you know. So you cannot keep track of all the redundant data pieces. That's bad. Okay, control, we can keep track of. So when we do updates, we can do the updates in the right way. Yeah. Control the redundancy. Yeah. So the question is, why you want to have control redundancy? Why we do not maintain the normalized data, right? Yeah. So let's answer the question here. Yeah. Why sometimes redundancy is not a bad thing? Yeah, here, let me describe, you know, the real world application when we need to use our data. Yeah. So the purpose to design our databases, we want to provide the business features for our business applications, right? Business features, all right, yeah. So you need to implement your business features in an efficient way. Yeah. So very fast, very easy. When you write a code, you don't want to make your code very complicated, right? Yeah. So serve that specific purpose. Yeah. All right. Performance consideration on relatively complex queries. Think about that. You may have the situation when you do the database queries, some of the queries could be very complicated. Yeah. That happens frequently. Some of the queries could be very complicated. Okay, yeah. Because yeah, the complexity of queries. Aaron is here. All right, Aaron. All right. All right. Complex queries. Why we may have complex queries, right? Yeah, yeah. Because the complex due to complicated relationship among data, among tables. Among many tables. Okay. Those tables are correlated. You need to consider all the relationships, right? Yeah. Then when you retrieve some part of the data, that could be complicated, right? Because you need to specify many different conditions. Yeah. Later, our next module, we will work on the database queries. We need to impose every time when we do database queries, find certain piece of data, we need to put a lot of conditions there. Okay, so that could be very complicated. All right, so when you have complex queries, then the performance could be slow. The performance could be slow. Response time could be slow. Okay, yeah. Then your customers won't be happy. Your real world customers using your web applications for your business, they won't be happy. So we click the button, waiting for several seconds. Yeah. So they are not happy due to your slow database queries. So you have to fix it. You have to make your database queries very fast. So very responsive. All right. For that reason, one way to solve that problem, you may need to store extra pieces of same data piece, but you put in a convenient, relatively simple table, so where you can retrieve those copies in much faster way. You can get around complex data queries using shortcut, simple, easy, fast queries. That's the typical situation we may have. Yeah, I had that experience before. Okay, so in my real world application development, yeah, when that situation happens, yeah, not frequently, but occasionally you may have that kind of situation. So then you may need to consider store redundant copies, some redundant copies of data for fast access. Yeah. So the performance consideration, you may need a certain redundancy. All right. The derived data comes from multiple tables. All right, so another case, derived data, not original data. Some data could be derived data. Okay, yeah. For example, the name of a student, we combine first name, last name. Okay? But in our table, we store the first name as under one column, last name under another column. Yeah, but in our table, we do not have one column containing both. Okay, yeah. So for the full name, that's the derived data. Yeah, we put two different columns together. So that's a simple example. Sometimes you may need to derive data using multiple tables to generate derived data. Okay. But because for the derived data, you may need to use some operations. For derived data, okay? Your operations could be complicated and slow, right? You need to spend a lot of time to generate derived data. Think about that. Another situation you may have in your real world applications, because you need to work on multiple tables, and you need to do a lot of data manipulations. That could take relatively long time. All right. After you generate the data, do you want to store the generated data or just use it once? But next time, if you use same derived data, do you want to run the same, those operations? Those operations, not very fast, not very responsive. Yeah, right? So this situation, better way, store the derived data in some other tables. All right. But the derived data, when you store somewhere, some other tables, that's redundant, right? Yeah. Because if you delete those tables, you can generate that part of the data by running the same operations next time. Okay. Yeah. But the problem is it takes a long time to get the generated data. Okay. Yeah. But for fast performance, you don't want every time when you access that part of derived data, every time you run long, expensive operations, you don't want to do that. Okay. So the quick solution, store redundant data. Use extra tables to store derived data. Okay. Yeah. But you need to control that redundancy. Yeah. First, you need that part. You need the redundant data. Yeah. But you need to control that redundancy. All right. Yeah. The queries to generate the data are relatively time consuming. All right. Even need some complex algorithms for data processing. Okay. Yeah. So then after you spend so much time, so much computing resource, you don't want to waste it. You don't want to throw away, right? So you need to store the generated data as redundant data. That's the redundant, but that's the good redundancy, right? That's the good redundancy. Okay. Yeah. So you need it. Yeah. All right. Faster access if we store it in a new table with redundancy. It's necessary. All right. So in your database design, think about that. You need to have that part. All right. Yeah. All right. So here, multiple table access with complex queries. All right. Replaced by single table access with simple queries. Yeah. So when you generate, you use multiple table, right? So this is the origin, the way you generate data, generate derived data. Yeah. So let me just, put derived data. Yeah. Here, access. Yeah. Access. Yeah. We want to bypass that, expensive procedure. Yeah, because this procedure, this expensive. All right. That is expensive. So access derived data. Okay. Yeah. Simple and fast. All right. Yeah. All right. So this procedure here, you can see we go the opposite direction. We add the redundancy. Our original data, there is no redundancy, right? But when we do this step, we add redundancy. So this step we call it data denormalization, not normalization. Normalization, you reduce the redundancy, right? Yeah. But here, you add a redundancy. Okay. Yeah. Denormalization, but it's necessary. Yeah. Because the performance is very important in your business applications. Yeah. Later, I will talk about the Google search. Google search is a good example. Google search, the response time very fast, right? Yeah, fractional seconds. Okay, 0 point something, right? Yeah. So later I will talk about, yeah, Google search. That's a perfect example for this data denormalization. Google search based on derived data, not original data, derived data. Okay. And the procedure to derive the data, very expensive. Very expensive. So then you have to use extra tables to store the derived data to make the user keywords-based search extremely fast. Google search. Yeah. All right. All right. B.3, data denormalization. Yeah. Okay. So that topic. Yeah. All right. The goal, simplify the computation. Yeah. Our algorithms to derive some critical, important business data relatively expensive. Okay. Yeah. Google search. Yeah. Later you will see one good example for this denormalization problem. Yeah. All right. View. So here, how do we understand this data denormalization? So we take this view. Yeah. So it's a space performance trade-off. Yeah. We are willing to use more space to get a better performance. We store derived data, we need to use more space. Redundant data, derived data, we need more space. But the benefit we have, we will get a better performance. So it's a trade-off. Okay. If you want to save space, you do not store redundant data, then you need to run that complex algorithms on the original data, but the performance is very slow. So you don't like that happen. Okay. All right. Yeah. So that's the view. Yeah. Use more space to exchange for better performance. Yeah. So that's a commonly used method in our typical real-world applications. Yeah. All right. Because nothing is free, the performance is not free. You need to pay. So here we pay more space. By more space, okay? Yeah. So more effort. Yeah. All right. With more effort for data consistency. Yes. But the gain, performance is the gain, right? The performance is huge gain. All right. But you need to pay. Yeah. So the space, so that's, one place you pay. Another place you also need to pay. You need to maintain data consistency. You need to pay some effort. Okay. Yeah. So we're willing to pay that part. Okay. Yeah. All right. A useful idea in applications. So here, let me get to the application part. Yeah. In real-world applications, the situation like this is quite common. Quite common. Yeah. So simple idea. Yeah. All right. So in the real world, we are willing to pay more effort to do pre-process. Yeah, here we take the pre-processing approach. Pre-processing. Okay. Yeah. Before we use the data, we do some preparation. Pre-processing for data preparation. you, okay, you know, based on the algorithm, right? Yeah. Example, Google search. Yeah. Here you may feel abstract. So what kind of pre-processing, right? You know, preparation based on the algorithm, too abstract, right? High level. Yeah. Google search will give you concrete examples for this idea. Yeah. Google search. Yeah. Next slide, my next slide, I will explain the Google search behind the scene. Yeah. All right. Yeah. Okay. Yeah. All right. So for the Google search, the pre-processing step, we do indexing web pages ahead of time. Indexing web pages. The goal, search all the web pages containing certain keywords in a fast, very fast way. Okay, yeah. But if you apply your search operations on the original data, extremely slow, extremely slow. Okay, think about it. You apply the search operations on the original data. Think about that. Apply the search, keywords-based search operations on the original data. Okay, original data, those web pages in the world. Okay, yeah, all right. So, yeah, so the performance gain is huge. Yeah, so here, all right, all right. Later, you will see very, very responsive. Okay, yeah, all right, yeah. So the original data, derived data. So here you can see, yeah. We need to generate a lot of derived data from the original data for the Google search application. Okay, all right. Yeah, so this slide, so let me explain the Google search a little bit. Yeah, so, okay, yeah. So here, the application is the famous Google search. Okay, all right. How to make each keywords-based search extremely fast, very responsive. All right, yeah. So the idea. Okay. All right. First, let me describe the original data. Okay. Yeah. So basically, all the web pages in the world. Okay. Yeah. It has the property, large amount, right? Huge amount. So the data amount, huge amount. Okay. Yeah. All right. Yeah. You can think about, yeah, the second property, you know, key words based search. String data. Data format, string format, string data. Here, why I emphasize the data format, it's a string format, okay? The reason for this format, we need to use the alphabetic order, right? Yeah. Or we can also call dictionary search. In a dictionary way search, okay? So you compare the first character, second character, third character. That's the alphabetic order, right? Dictionary search. Yeah. Dictionary search. Slower than numeric search. When you search numbers, much faster. Okay. Numbers, you just search based on the numerical value. It's not a dictionary search, all right? Dictionary. First character, second, third, you know, much slower than numeric based search. All right. So the property, okay, now. So the original data, all right, okay. Derive the data. Okay, yeah. So now, prepare the data for fast search algorithms. So the goal, prepare the data for later fast search operation. Okay, yeah, all right. How? Yeah. How? Okay. All right. Spider crawling, right? Or spider, little programs, okay? Some small programs visiting web pages. In the world. Okay, spider crawling. How to spell? Crawling. Sorry, yeah. Yeah, so you know that. Yeah. All right, spider crawling on web. Right? Yeah, so that kind of story. Yeah. All right. A large number of spiders. Okay, yeah, all right. The data processing time is quite long. Yeah, okay, quite long, all right, yeah. Then conversion, data format conversion. Okay, yeah. String data to numeric data. Because numeric indexes, right? Each keyword, one keyword becomes one index. Indices. Okay. Keyword. Okay. So one keyword, it has a numeric value, numeric ID. Yeah. Keyword becomes numeric ID. All right. So then, yeah. So here the conversion, regarding to conversion. Yeah. Keyword. Oh, yeah, so here it's pretty slow. Yeah. All right. Keyword. We know keyword is a string, but we map to numeric ID. ID is a number, right? ID is a number, right? All right. Web pages, one web page. Web page, we know the original reference of each web page, URL, right? Yeah. URL, that's string value, right? Yeah. But we map to numeric ID. Each web page, there is a numeric ID, okay? All right. Then, when you do the string data type search, original, after conversion, you do the numerical based search. You know, both numerical values, okay? Yeah. Which web page contains this particular keyword? The web page, you have a numeric ID. The keyword, you have a keyword ID, okay? And there is a mapping between them, association. The keyword ID, web page ID, you establish relationship, mapping between them. That's the derived data. Okay, that's derived data. So this part, derived data. Okay, so you know, yeah, derived data. That mapping, derived data. Okay, yeah. Then next time when a user type some keywords, then they just use the numerical values to do the fast mapping relationship and return the search result extremely fast. Think about that. That kind of pre-processing, that kind of derived data, that kind of redundant data, right? Derived data, redundant. But you need that redundancy. Okay, yeah. All right, so this is a good example. So this is a perfect example for our data normalization concept. Okay, yeah. All right, yeah. So next slide, yeah. Responsibility for control the redundancy. Because we need to maintain data consistency, right? Yeah. Who has the responsibility? Yeah, so this slide, so let's look at that question. All right. Someone is responsible for maintaining controlled redundancy. Okay, yeah. So here we need to look at this someone closely here. Yeah. All right. DBMS is the first object we should consider. DBMS should have the capabilities to control. Yeah, so this sentence I took from our textbook. Should. So look at this word should. All right, yeah. Have the capabilities to control this redundancy in order to prohibit inconsistency among the files, but it couldn't. Okay, couldn't. DBMS cannot make it because it's too hard to maintain this kind of controlled redundancy. It's too complicated. DBMS cannot do it. But in future, AI becomes more and more powerful. That could be possible. Okay, yeah, relying on AI, strong AI advancement, then this kind of control redundancy could be possible. Yeah, yeah. But at this point, DBMS cannot do it. Okay, yeah. All right. Yeah, so this one I took from the textbook. Yeah. But what DBMS can do, yeah, something too advanced, DBMS cannot do it. The DBMS can do enforce certain constraints or relatively easy constraints. Enforce straightforward, easy constraints. That DBMS can do. Okay, all right. Cannot enforce business rules directly. Yeah, we know DBMS, they are general purpose. The DBMS you can use for all different kinds of business in the world, but usually the DBMS, they do not understand your business. They do not understand your business rules. And you cannot require DBMS understand your business rules. Okay, yeah, all right. So it cannot enforce business rules directly for you. Okay, yeah. But this kind of control dependence, you can see connect to the business rules. Okay, yeah. So the responsibility of application programmers, then the application programmers, they have the responsibility to write a code to enforce the control redundancy. A lot of work. Okay, no. So many programmers, so you can imagine in Google team, in order to make sure that derived data, put the derived data under that controlled dependency, control the redundancy. Yeah, a lot of code need to be written for that purpose. Yeah. Okay, all right. Yeah, okay, yeah. So that's the topic I like to cover for today. Okay, yeah. And I also noticed, so today I finished all my slides, but when I check my a few lectures before, I noticed a few lectures, part B and part C, module 1, I have one slide left for part B and part C. Yeah. So later I need to find some time. Yeah. Oh, yeah. So this student, okay, yeah. Later I need to put some time to, complete those 2 slides. Okay. Yeah. One slide for each module. So I try to spend because I noticed some useful information there. Yeah. Because when I make the quiz questions, quiz number 1, yeah, some of the questions I cannot give you because I didn't cover those 2 slides. Okay. Yeah. So that's another reason. Next time I try to find, at the end of the lecture, I try to find some time, cover those 2 slides. Okay.